Hello everybody. Before I begin the talk today, I would like to say that if any of you have any questions during the talk, please just blurt them out and raise your hand, whatever, because it might get complicated fairly quickly, and I don't know what to properly explain or what not to. So that said, I am Chiel Douwes. I'm a student at the Hochschule Utrecht in the Netherlands, and you may know me from the role of Chiel if you have seen Odin's talks. I'm also the maintainer of Quasar MPL, which is the current fastest meta programming language, or stable meta programming language. And I'm also maintainer of MetaCheck, which is a compile time unit testing library. Today I will be talking about allocators, which is also a subject I've been researching. And yeah, that's today's talk. So, why do we need allocators? There is So a lot of applications need a variable number of elements. So for communication protocols or such, you may not know how many messages or elements you get, and that is why you need a variable sized buffer to hold those messages. There are multiple ways of dealing with this. Mostly it's done by either putting objects on the heap or creating a special pool or object to hold those messages. These are the most common solutions. So you have either a pool, which is holds only one type of element, and then from fixed buffer, which is pre-allocated in memory, or you have the heap, which is basically allocated in all the available space that is left after the stack. So that is a global object. There's also some variations on the heap allocator. I will go into those into a moment. First of all, let's take a look at the pool. So as I said, it's only a single size, and it's pretty much always a fixed number of elements. There are some pools which can vary in size, but those are pretty rare to see. Heap, you can put any size of allocation on the heap. So whether it be the entirety of the memory you want to allocate or only a single byte, that is or should all be possible on a heap. And you can also, of course, allocate any number of elements. There are two main variants of heap allocators. Generally, it is either a linear allocator, which means that allocations are put immediately behind each other in memory. So if you allocate a 5-byte element and then a 3-byte element, those memory or pointers will always follow each other exactly. And then there is the segmented allocator, which is most common nowadays, which splits the memory in multiple parts to get a better behavior out of the memory. The main reason for doing this splitting of memory in segmented allocators is for a reason called fragmentation. So there are two main types of fragmentation. Fragmentation caused by how elements are allocated, in what order, in what size, and in what order they are deallocated. It's also a reason. And it is generally called external fragmentation. So fragmentation caused by allocations themselves. And then there's also internal fragmentation, which is fragmentation caused by the allocator itself. So that will be in segmented allocators, where the allocator itself adds extra space behind elements to fulfill some property of the allocator itself. If you want to know more about these types of fragmentation, about how heap allocators work, different types, I would suggest having a look at Andreas Weiss' presentation. He did a great job at explaining what the different types of allocators are. Since I will be talking about special allocators here, I will not be covering all the different types and stuff. I will be going through some of the previous work on segmented allocators. So first of all, the most basic type of segmented allocator is, well, the most basic type will be a pool allocator, because that only has segments of one size. But a normal heap allocator would be a buddy allocator, which splits the memory that is available recursively into two. So for instance, if you have a memory size of 16, then the buddy allocator would split that into 8, and then into 4, and then into 2, and single bytes. So every time you do make an allocation, for instance, if you would make an allocation of size 3, it always gets increased to size 4, because that is the next size up. And then there's the Fibonacci buddy, or the Fibonacci allocator, but I like to call it Fibonacci buddy, because in the Fibonacci allocator, the sizes of the splits are not equally distributed. So in the buddy allocator, a block of 16 will be distributed in 2 blocks of 8, but in the Fibonacci allocator, it will be, say, a split of 13 and a block of 8. And finally, there's the slab allocator, which is normally used in the kernels nowadays, like the Linux kernel. And that is basically a free allocator. A slab allocator is basically a linear allocator in sizes above the cache line size. So the memory gets segmented in blocks that is the size of the cache. And lower sizes than that will just get subdivided by the buddy allocator. So here's an example of the buddy allocator. As you can see, 16 bytes subdivided. Is that? Yeah. Okay. This is not a true a true Fibonacci allocator would be somewhat different, because the purpose of the Fibonacci allocator is to get as even distribution of block sizes as possible. So it would not use these exact numbers, but a more even distribution. So why do I make another allocator? Why are these not good enough? Let's take a look at my specific use case that I made the type-based allocator for. So many times you only want to allocate a certain amount of types. So for some communication protocols, for example, you only have packages of 8 bytes and packages of 4 bytes. So you only need to be able to allocate 8 or 4 bytes. And then, of course, you would need to have any number of elements, because it would need to behave like a heap, of course. So what options are there for this use case? you could either create multiple pools for storing the 8-byte objects. So you create one pool for storing 8-byte objects and another pool for storing 4-byte objects. But if you run out of either of those pools, then you're essentially out of memory because you cannot use any more of the memory in those pools. And then of course you can use the heap, but that also has its drawbacks because of heap fragmentation. But whether it be the external fragmentation caused by linear allocators or internal fragmentation caused by the segmented allocators. Now, there are some assumptions made in segmented allocators that that are essentially not needed. So the heap allocators assume that you always want to be able to allocate any size of element. And it also assumes that a certain allocation order or things like that. Or in the case of a slab allocator, it assumes what your cache size is. So what if we take those assumptions and change them?
Are these the assumptions you make or other allocators?
These are the assumptions that are, so the question was, are these assumptions I make as user or made by the allocator itself? These are assumptions made by the allocator itself. So if you have a buddy allocator, it would assume that you want to be able to allocate any element from size 1 to max memory. But that...
So allocators in general make these assumptions?
Allocators in general, yes. Or heap allocators in general. So that's where type-based allocation comes in. Basically, when you create a type-based allocator, you first specify which types you want to be able to allocate. And then, based on that, you build an allocator that it uses those sizes to reduce the fragmentation in the allocator. So, I'm going to talk a bit about how this is implemented. First of all, how does the basic premise work? How are these types combined? What process is that? And then a bit about the different components that are used to get those combinations. About the tree structure that is made from those components and the algorithms used to combine everything into that tree structure. Okay, so first of all, what exactly happens when you create a type-based allocator? So say, for example, you want to create a type-based allocator with a element of size 3 and a type of size 4. Then you would create two pools. One pool for creating objects of size 3 and another pool for creating objects of size 4, and get those pools to as closely match each other's size as possible, and then put the pools in a union so that you can allocate either pool. So that would look something like this. As you can see here, the pool A, first pool, has 3 elements of size 4, and the second pool has 4 elements of size 3, so they're both allocators or pools of size 12, which is then put in a union, and that union is also size 12, so you would be able to create multiple of those unions to either get either pool.
When you say a union, does that mean like if I now allocate the first A, the leftmost A, that would block the 2 leftmost B's because it comes from the same member?
Yes. So essentially you only get one pool. If you want to get the B type, then you create a second union and then use pool B.
Okay, so once I've taken the first A out, I cannot get any B.
You cannot get any B. Okay. So as you have seen, there's several components there. So you have the basic pool types, and you have the union types, and then of course you need to combine them in a way. So I'll talk a bit about the different parts that go into it first. So you have the identity allocator, which can only allocate a single element, which is, it's basically the type, but then wrapped in an allocator. And then we have a union allocator, which can allocate one of several types. A pool allocator, which can allocate several of one type. And finally, we have a segmented allocator. This one is kind of special, because if you have multiple pools for a single type, you need to be able to connect them somehow, because otherwise you would not be able to know in what pool you have to allocate new elements. So I'll go into that a bit. First of all, this is the basic structure for the code. This may look a little confusing. In this case, it's an example for the pool allocator. The basic reason for the code looking like this is that you need to be able to create this tree structure of different allocators. So because the root nodes need to access the data type of the allocators below it, we have like the data type available in the allocator here. So for example, this pool allocator, as you can see, it has a data type of a pool. So whenever it says I want to allocate a pool, the parent allocator can say, okay, I can allocate a pool, and then give it to this allocator. Beside that, we have the standard functions. So we have the allocate function, free function, which both take the type of the type you want to allocate. And then a special function, which is lookup type. This is needed because normally in an element, if you want to get the corresponding pool for an element, you wouldn't be able to do so because you don't know where that pool starts. So to be able to search what pool an element belongs to, we need this function. So a bit about the allocate function. As you can see, it's a tag dispatch function, which basically means that as the first parameter, we use a tag type, which is an empty type, which you only instantiate to create or change which function you call. So that is how you specify what type you want to allocate in the allocate function. This is also especially useful because the entire tree structure for the allocators is based on inheritance. So the entire structure then has an overload set of all these allocate functions, and you choose out of them based on the tag type. And you may also have seen like the inheritance structure looks a bit complicated. It uses a curious recurring template pattern, which is a pattern to be able to access parent classes from a subclass of inheritance. And this is needed because the child allocators need to be able to allocate from the parent allocators. So we need to be able to pass the type it has to allocate from in some way. And of course, the upper allocator also needs the data type of the lower allocator. So we have this bidirectional dependency that we need to solve. So this is the CRTP type, or this is how it's done. As you can see, the sub-allocator always gets past the type of the current allocator. So in this case, type superalloc is the type here. So that gets instantiated, and then it gets passed into the child that is inherited. Is that?
Superallocator, right?
Superallocator is then, that is also passed from the upper allocator. So it's just like the type here is passed into the lower allocator, the superallocator is received from the level above it. Yeah.
Can you explain again quickly what the exact semantics of the sub-alloc is? The outer temperature?
Yes. The sub-alloc, basically because you want to create this tree structure, you need some way to define it. So if you say, I want to have a pool allocator that can allocate unions of these types, then you would say a pool allocator, and then as a sub-allocator, a union allocator, and then as sub-allocators of those, you would have identity allocators. So then if you allocate one of the types of the identity allocator, that goes to the union allocator, ask it, hey, can you allocate my type? And then the union allocator goes to the pool allocator and asks it to allocate a type for it.
So in that case also the sub-alloc colon data T would be a union data type.
Yes.
Yes.
Okay. Really quickly, this is the lookup type function. This is the part that I'm most unsure about in the entire library. If any of you know if this contains undefined behavior. Yeah, that's everything. So no explanation is no needed. Yes. Okay, so identity allocator is really simple. When you create an identity allocator, it doesn't actually include a function to allocate elements, because the identity allocator itself does not know where to put types into memory. So that is also the reason we have the data type member, so that the parent allocator can know what types it has to be able to allocate for this allocator. So the identity allocator is basically an empty class. It only specifies a type, but it doesn't know how to allocate or how to deallocate or even look up where its types are. And we have the union allocator. Yeah.
So I'm trying to wrap my hands around this. If I want to allocate something, do I start with a leaf and then propagate up as needed?
Yes. You start by you start by just calling the identity allocator. You call the allocate function of that identity allocator. So then the identity allocator, because it has received the parent allocator through CRTP, it calls its allocate function, and then that allocator also calls another parent allocator, and so on until you reach a proper memory location. Yeah. So it's basically the same for a union allocator. It doesn't really know where to put allocations, because it is just a union. So a union allocator can have multiple children, and it will create a union of those different data types for the children. So it looks like this. You specify the sub-allocators, so the children, and then the data type that results is just a union of all the data types of the children. And also, as you can see, a union inherits from all these sub-allocators. So all the allocate functions of the sub-allocators are available through that inheritance. We have the pool allocator. That basically only handles one type and some amount of elements. It's fairly important that the amount of elements can be changed easily in the interface, because it's a basis for the algorithm to figure out how to best lay out the data. In this implementation, I use a bitmap allocator, which is basically a pool which has a single byte in front of the pool to indicate for each element whether it is free or not. So if single bit in a bitmap allocator indicates for a single element whether that element is free or not. And using this single byte or single integer, you can also very easily tell if a pool is fully empty or if it is fully full. So that is the reason a bitmap allocator is basically the only viable pool for this structure. Because we need to create the segment. This is basically the list of pools I talked about. The segmented allocator basically keeps track of which pools have been partially filled. And whenever you want to allocate a type in this segmented allocator, you will look at the first pool in the list and just allocate an element from that pool. And whenever a pool in that list is either fully filled or fully empty, it gets removed from the list. So all pools which don't have some amount of space in them are not contained in the list, the free list. It's important to note that this list also has to have a head pointer. It might not be immediately obvious where to store this head pointer, because the data type can be allocated multiple times, but you only need a single head pointer for the list of pools. So that would be in the global storage. It's basically part of the global allocator object that you put somewhere in memory. Looks like this. So basically in the type, this is the type that gets instantiated as the actual allocator type. So you just put the head pointer in there and then it just works. Yeah.
The n, is that the number of bytes or is that the number of elements?
That is the number of elements.
So then I have a follow-up question.
Yes.
Because if I imagine I have a union of A and B, right? And A is 3 elements and A is 3 bytes inside and B is 4 bytes inside. Then if I want to play this neat trick that you showed in the beginning, where I can get more A's and less B's from the same amount of memory. In the end is the number of elements. I always need to account for enough memory for the biggest type, right? So, like let's say I have the B is 4, right? And then if I have like 12 bytes backing me up, I can fit 3 times a B in there.
Yes.
I could fit 4 times an A in there.
Yeah, so you're asking how do you see, or how do you increment this number to get the different pool sizes to match each other?
Exactly,
Yeah. I'll actually go into that in a bit.
okay, so
That's,
that.
yeah, immediately after this. Okay. There is one more thing I need to cover before going into that. The root allocator. So for this entire tree of allocators, you need to have some place to actually put all the data, because otherwise you just have a theoretical data type, but no location to store it. So that's the root allocator. Basically, you have a specific type which knows where to put the memory, and it doesn't have any upper allocators to ask for more memory. So for instance, it could be a pool, and you put the pool either on the stack or in global storage or on the heap if you want. And yeah, that basically goes in the same place as the head pointer will go. Just in the allocator object itself. You could also do something funny with the root, and that is you can have the root be a heap allocator. So you can use the operating system heap to allocate these pools or pool segments, and that way you can still save some memory while using the entirety of your operating system memory, basically. This may also help. Yeah.
That you're basically putting the system allocator out of business. So you just allocate your thing and do your own algorithm.
Yeah, you build the entire structure, and then it results in some union or some pool, and then you ask the system allocator to allocate that pool for you. And so you basically keep allocating pools on the heap. And because it's this special, specially made structure that is supposedly less fragmentation, that would then also mean that you get less fragmentation on the heap. And it would also do things like improve cache locality, because all the pools are contiguous memory. So the objects on those pools will be in closer in cache. Okay, so let's talk about how to create the allocator structures. How do you get these pools and get them to be the correct size for the lowest amount of fragmentation possible? And there are some limitations you have to consider when creating algorithms that do this, because for one, compile time is a huge issue. Templates that are used to do this are not known to be very fast. And there's also the problem of instantiation depth, and memory usage. So the complexity of algorithms you can create is fairly limited in that sense. Okay. First of all, let's see how to create a simple union of two pools. So you want to allocate two different types and have this structure be this low fragmentation structure, like in the example of the 3 and 4 byte objects. How do you do this? Well, first of all, you create the pools for the different objects. You start with a size of 1, because you need to have at least one element in the pools. otherwise you cannot allocate anything. And then you iterate or keep iterating until you reach some maximum size that the pool can handle. So for instance, in the bitmap allocators, the maximum size would be the size of the system bit width. So if you have a 32-bit system, you can only have 32 elements in a pool at maximum, because otherwise the lookup for which elements are free or whether the pool is empty or full would be quite a lot slower. So you keep implementing the smallest pool, and for each time you increment, you add that combination of two pools to a list of potential candidates that you are going to go through later. And after you have done that and reached this maximum size that the pool can handle, you go through and score each of the combinations of pools. So for instance, in the 3 and 4 byte example, you could have a pool which is 4 elements and 3 elements, or you could have a pool which is 5 elements and 7 elements. And in that case, the 4 and 3 elements would be scored better because it has a lower disparity between the sizes of the different pools. And it would also have a lower size. So the reason that size is important for these pools is because otherwise you will end up with very large pools to get as low fermentation as possible. And it's generally not wanted. You may have a situation where you do actually want very large pools to get as most memory out of your system as possible. So that could be changed, but it's not generally useful. Now, a full algorithm, this is an implementation of a greedy algorithm, so it doesn't get the perfect results. As I said, to get perfect results, you need a far more sophisticated algorithm, and that's just something template networking can currently not handle. You will run out of memory on your compiler far before you ever get close to finding a perfect solution. So there are several trade-offs to be made in this combination algorithm. So in what order do you search for pairs of allocators or pairs of pools, and how deep do you want your tree structure to be? Things like that define how you want to have your allocator be constructed. So this is pretty much the most simple algorithm you can make. So you just take all the combinations of pairs that you have. So for example, if you have a list of 3 types, then you have 3 combinations of pairs. You run the 2-type algorithm on all those pairs, and you see which has the best score out of all of those. And you add the combination of those types back into the list. So you take the 2 types out of the list and put the 1 type back in. Yeah.
When you say best tier, is that with the most similar size, or what is your metric for good tier?
Yes, so with the lowest disparity between the pool sizes. So just like in the situation of 2 types, you score each combination of pools with a certain number. You basically use that number as a score in this.
That's basically the size of the unit, right? Union of types.
Yes, but if one of the pools in the union is smaller, which may happen, it's not always guaranteed that both pools are the same size.
Yeah.
So if, for instance, you have a 1 byte difference in pool sizes and your total size of the pool is something like 20 bytes, then you have a 1 byte score and then divided by 20. I can't remember the exact scoring system, but it is based on that difference and then also the size of the total. Yeah.
Maybe my train of thought is wrong here, but wouldn't it also be a good match if like the size of one pair evenly divides the size of the one?
Yes, so you can have a pool which is just one element and then another pool which is a multiple, so that it comes to one size. So it's actually fairly common to have elements of size 64 and then elements of size 16. So you would have a pool just or a single element that is the 64 element, and then a pool of 4 16-byte objects. I'll give a quick example of how this is done to better understand the algorithm. The example here is a point cloud octree. It is often used in things like point clouds for land surveying or recreating 3D models out of multiple photos. And this octree structure is useful because you can do very quick queries about what is the closest point to a certain location, or what are all the points adjacent to a certain plane or in a certain area, things like that. The points in this point cloud have 32-bit precision, and they include X, Y, and Z coordinates and also colors. I assume the colors to be also be 32-bit. I know that's normally not the case, but for this example, the math works out better, so you'll just have to bear with me. So in this example, we have 3 types. We have the octree node, which is a node of 8 pointers. Each of the pointers, which is either another octree node or a point. And then we have the point itself, so with the coordinates and a color, comes out to 24 bytes. And then the variant, because you need to have a structure which tells you which of the 2 types is stored beneath that pointer. That will be a tag byte and a pointer, but because of padding, because of memory alignment, it comes out to be 16 bytes. You can run the same algorithm with packing enabled. For those of you who know, packing is a way of getting a memory to be unaligned or types to be not aligned in memory. So that is something you can do. The algorithm supports it, but I don't recommend you do it because it may have various side effects. So here you see different types, sizes, and then we create the combinations. So each of these pairs have a combination, and then we score them. So these are the sizes of the resulting pools, and they all have 0 fragmentation, so there's no other penalty here. As you can see, the point variant is the lowest size pool, so that will be chosen in this case. And you continue the algorithm with the 2 remaining types, which is only 1 type that can result from it, because it's only 2 types. So in the end, this one single type is your result from the algorithm, and that is what you actually allocate when you put it either on the stack or on the heap or somewhere else. So this is the tree structure in, yeah.
To understand these numbers, you basically you calculate what would the size of the union be for the different combinations,
Yes.
and then you choose the one that gives you the smallest overall size.
Yes, you try all combinations of pool sizes until you find one that gives you the best amount of fragmentation, and then it's scored based on the total size of that union.
And the size of the individual pool of the leaves, that is basically determined by the size of the type?
That is the size of the type itself, yes.
And the number of elements, which is an input from the user?
Well, that is determined by the algorithm. So, oh yeah, okay, I didn't put it in here, but these unions would have, before the identity allocators, so before these types, they have the pools in them that have the different sizes. So for instance, the union of 48 bytes would have 2 of points and 3 variants. So it is a union of 2 pools of either 2 elements or 3 elements. And the union of 129 bytes, same way. Yeah.
The 192 could have been any multiple of that also. So how do you
Yes, it could have been any multiple of that, but then it would be bigger, so it would be less flexible, because it's penalized for being bigger.
Oh, okay. So you always take the lowest
Yeah.
possible size.
Yeah. Okay. Is that? Yes.
Optimization, does that happen at runtime or at compile time?
At compile time, yeah. It is theoretically possible to do this at runtime, but then you would need to store the sizes of the objects and this entire tree structure at runtime, so that would need more memory to actually store it. Really quickly, because I'm running out of time. These are some other examples. You can use it for communication protocols, often have fixed sizes. Entity systems, like in games programming, entities often have fixed sizes. So the interface, how you create a pool. This is basically, the combination algorithm itself is a function, so you can use it in metaprogramming and other integrated systems. So if you, for example, create a state machine, you can collect all the types in your state machine and create an allocator out of that automatically. So finally, you assign a root allocator to the created type or created pool that you have here, and that root allocator you just put somewhere in memory. So this alloc can either be on the stack or in global or heap, so and so. Because the allocate functions, you've seen these before. This is basically an example. It's fairly simple. There are some more possibilities that can be done with these allocators. So for now, it is not possible to use them, for instance, in a standard container, because you need to specify the types beforehand, and standard containers have lots of internal types that you cannot know beforehand. We do have polymorphic allocators, so you could wrap the allocator types in a polymorphic allocator. And the problem is that polymorphic allocators use a size as the allocation type instead of the types itself. So you would need to do some translation from size into type to get that to work. And also the Destructor does not include a size or a type at all, so it would be impossible to know where to deallocate your memory. Or you need to do tracking where to have it. Oh, so it's time. Yeah. Polymorphic allocators also have virtual functions. So if you're in an embedded system, you probably don't want to use virtual functions. It's another drawback. Rebind, skip that. Stateful Matter programming. There is a way to automatically gather the types you need in your allocator. It's called Stateful Matter programming. It is all the behaviors that stateful matter programming use are defined by the standard, but it itself is not defined. So it may or may not be UB depending on how you look at the standard. And I believe there is a movement to completely remove this from the standard. But with stateful matter programming, you could, in theory, take all the allocations that are made in your program, and then at the end of your program, you instantiate a special allocator using only those types. Some improvements in combinators. If meta programming improves and becomes faster, it would theoretically be possible to create an optimal allocator, so which it reduces fragmentation as much as possible. But of course, there is always the trade-offs you have to make between tree size and other trade-offs. And then also you could have heuristic-based algorithms, which use a different scoring system to speed up the process of creating these allocators. Okay, so a bit about the practicality of these allocators. As you can see, this slide is empty. Now, you may have heard, like, okay, you can improve your cache locality, or you can get better fragmentation, something up to 10% better fragmentation, or you can get better guarantees, compile time, everything. But in the end, it is a trade-off of what you, or if you actually want to use these allocators, because it cannot be used with standard containers. You have to specify the types. It's pretty cumbersome to actually get in your program because it is all fairly manual. Beside that, I do think it has its merits, not only as just an allocator, but also as an example of what you actually can do with metaprogramming and what direction C++ as a whole is heading in. Because things like this are possible to do with metaprogramming, and there are a lot more of these things that will be possible if metaprogramming improves. So, yeah, again, the improves. With great reluctance, I give you the link to where the actual code is. If you want to have a look at it, go ahead. But I would greatly recommend that you do not use it in production code. I still have not figured out whether that lookup function is UB or not, so there you go. Yeah, that's everything. Thank you very much for listening.